Good morning. You can turn off the screens of your computer. Let's get started with the lecture. So here's the sign-up sheet, and also please pass the lab. You have your lab with you. Did you
I think Matt has it.
Okay, so he's not here. So if you doesn't come today, try to find him and bring him to my office. You want to get those points. Um, were you able to verify the solution with Excel solver? No. So what was the answer? The end. What was the value of x? X1 equals 2, x2 equals 0, x3 equals 1. Okay, so let me go over that really quick. Okay, so the first part we did it in class. So we did the formulation for the first phase. We added one artificial variable. From there, we created the first or the initial tableau. And you notice that your basic solution only, well, part of it is denoted by the artificial variable, and you have one slack variable for the first row. So the first one was to just make these numbers 0. So easily you can just go multiply this row times 1 and add it to the first or this row 0, and you will get this tableau. Okay, so that's your initial tableau with your basic variables, S1 and R2. Okay, from there you have two variables, and you need to find out if you can enter a new variable for your basic solution. So from here you can see that x2 has the largest maximum or the largest positive value. So we know x2 can enter the solution. Now we need to find out which of the two variables will exit. So from there you do the ratio using this column and this column, and you can choose either one, S1 or R2, to leave the basic solution. So I chose S1, so I enter x2 to my basic solution and did the corresponding row operations, and this is how the tableau looks like. Okay, so this tableau is open, right? But the problem is we still have a artificial variable in our solution. So R2 equals 0 is a basic in the phase 1 solution. So the next step is to find out how to take that artificial variable out of the basic solution. So you can choose either one of the variables that are not part of the basic solution to enter the basic solution. It could be positive or negative. Okay? So from the variables that we have, x1, which is not part of the basic solution, x3, and so on, I chose x1. So I'm going to use x1. I want to try x1 and see if I can get rid of the artificial variable. So x1 is going to enter the solution, and I'm going to pivot R2, right? Because it's the variable that I want to take out of the basic solution. So the first step is to make this -5, 1. So you multiply times minus 1 over 5, and you get this row. Then you do the corresponding row operations to make these numbers 0 and this one 0. And this is how the tableau looks like at the end. Okay, so now you have an optimal tableau, and you have your artificial variables out of the solution. So with this tableau, you can drop R2, the R2 column, and go to the next phase, which is phase 2. Were you able to get here to this point? Okay. Any questions? It's clear what we're trying to do, right? We're trying to take this artificial variable out of the basic solution, and we were able to by adding x1 to the basic solution. Okay, so now in phase 2, what I do is I use the same tableau. I drop R2, so R2 is not here anymore, and I change the values for the row 0 because now I want to use the original coefficients from the objective function. So I have -2, -2, and -4, and in this problem we were maximizing, right? So before you do the steps for the simplex method, you need to find out if the solution that you have or the tableau you have is consistent with the initial tableau for the simplex method. So you have your basic variables, x2 and x1. You have the coefficients for those two basic variables, but you see that here, those two coefficients are not 0. So before you implement or before you start solving the problem using the simplex method, you need to make these two numbers, or these 2 minus 2, 0. Okay? So this is what I'm representing in this table here. So the first step was to make these numbers 0. So you perform the row operations using this row and adding to this row. We'll still have x2 with -2. So we perform the same operations. Until we get to this tableau, right? So now we have our basic variables with 0 coefficients in the row 0. And now we're able to, using this tableau, we can start implementing or solving using the simplex algorithm. So you're maximizing, you're going to enter the largest negative value. So that corresponds to x3. So x3 should enter the basic feasible solution. And you do the ratio using these coefficients in the right-hand side, and you find that the ratio, the minimum ratio is 0. So x1 is going to leave the basic solution, and x3 is going to enter. So that means that x3, the coefficients for x3, this and this one should be 0, and this one should be 1. So if you perform those operations, this is how the tableau looks like. Okay, so this is the optimal tableau. That's it. x2, x3. So there's no more negative values in our solution. So x2 equals 2, x3 equals 0, and x1 equals 0 is our optimal solution. So the objective function is 4, x1 equals 0, x2 equals 2, and x3 equals 0. Any questions? Yes.
What were those two steps you did, like at the first step when you first got the phase 2?
This on the second phase?
Yeah, like the first couple steps.
Here?
Was that just normal solving, or was there a reason why you made x1 and x2
These two?
Yeah.
This This is coming from
Yeah, I know I got there.
Yeah.
Why did you take the step after? When you pivot?
this step.
No. Starting here. Why did you not?
Oh yeah, because remember these are the basic variables. You're using the coefficients from the original objective function, but these two numbers needs to be zero in order for you to implement the simplex method. Because you have to be you have your basic variables, your basic variable coefficient needs to be 1 for the corresponding variable, and in row 0 they need to be 0 in order for you to apply the. At this point, the tableau is not in does not satisfy the requirement for starting the simplex method. So for you to be able to implement the simplex method, these coefficients need to be 0.
Why did
Because x3 is not a basic variable. So at this point, these variables are basic, but having those two coefficients here does not make them basic because you are entering a new objective function. So in order for you to have them to satisfy the requirement for being basic variables, those coefficients need to be 0.
Okay. We already know that?
Yeah.
Okay.
Yeah. Yeah, we did it for all the examples. Yeah. Okay. Yeah, so you need to be sure that when you get to this part, you have to make those numbers 0. Actually, I can show you here. This is here. So this is for the M method. We did the same thing. We found that R1 and R2 were part of our basic, but these two coefficients are not 0. So before proceeding with the simplest method, computation of rows of the 0 must be made consistent with the rest of the tableau. So the right-hand side of the 0 should be 0. To eliminate the inconsistency, we need to substitute R1 and R2 in the 0 using these operations. So that's why we started the method by making those coefficients 0. And the same was applied to the two-phase method. So here, they're basic, but the coefficients are -1. So the first, you need to make them consistent. So we went from here to here, and then we started the method phase. Okay. I guess that will answer some of the questions that you will have for the homework. Yeah. So let me go to the homework. Okay, so the first problem was to consider these constraints and then solve the problem for each of the following objective functions, which are the same, but one is minimizing and the other one is maximizing. I guess the other way around. So you start with maximize and then minimize. Okay, so we have our constraints. Let's start with maximize 2x1 plus x3x2 minus 5x3. So I'm going to use the M method. So for M, I'm using 100. And since we are maximizing, starting with M equals 100. So the first tableau looks like this. No, you have to. You can use a large number. It will matter. I mean, it has to be large enough when you compare them to the coefficients of your problem. So if this is 100 here, you don't want to use 100 because the penalty would not be enough. So in these cases, you see the coefficients are very small, so 100 will make a difference. Okay? Because what you're trying to do with those coefficients, remember, is to, if you're maximizing, you want to penalize. I guess I'm not able to write here. So you want to penalize the objective function. Your objective is to maximize. You want to put a penalty, so you're going to subtract minus R1 minus 100 R1 minus 100 R2. That will decrease your objective function. So that's the penalty. Okay? So when you move those coefficients to the left side, that's why these two numbers are positive. Okay? So this is your initial tableau for part A. So from here to here is what we were discussing. Like you have to make these two numbers 0 in order to start solving the problem. So that's what I'm doing from here to here and from here to here. So I make those two coefficients 0. And now I'm able to start solving the problem using the simplex with the artificial variables. So you start with your two artificial variables. Since you're maximizing, you want to enter the largest negative value. And that will make x1 part of the basic solution, and R1, R2 will leave based on the ratio. So when you continue solving the problem, then at the end you will have x2 and x1 as part of your solution and this number. So again, here what I'm doing in order to solve this problem really quick is I'm using Excel. Basically, I'm performing these operations with the computer. You can tell Excel to show you a fractional number. This time for the next exam, I'm going to try not to have fractional values. So I'll make the problem so you can solve the problems with integer numbers. So, but I know it's very hard for us to solve those numbers with fractional numbers. So when you perform those iterations, then you get to the solution. And the same thing applies for the second part. It's just you need to modify your row 0 because now you are minimizing. So the coefficients, the penalties are going to be positive. So when you enter them in the tableau, will be negative. Okay. So again, you're maximizing. You're using the artificial values to impose a penalty. So when you minimize, you maximize, you use a value 100 R1. That will impose a penalty because it will decrease. If you have a value for your artificial variable, that will impose a penalty. It will decrease your maximum solution. When you're minimizing, it's the opposite. You are adding that. right? So when you go to the tableau, remember this is z equals. So when you go maximize, this is going to be c minus x1 plus 800 R1. And when you minimize, this is z minus x1 minus 800 R1. And that's why when you are minimizing, these numbers are negative, because they are coming from this objective function, in which you have the penalty as a negative value. So once you have your initial tableau, you can solve the problem in the same fashion, and you should be able to get the objective function and the decision variables. So again, before you get started with the method, you have to be sure that these numbers are 0. Any questions?
Scroll back up.
Sure. To the first.
Whenever you so when do you decide that x1 is the basic variable? When do you put it in the basic column?
When do you put it here?
Right.
Because when you decide which variable is going to enter the solution, right? So you know x1 is going to be part of your basic solution now. You don't know where. You don't know if this one is going to leave or this one is going to leave. You know one of the two is going to leave. So you decide which one is going to leave based on the region. So the minimum one is the one that is going to leave the solution. So this one is the minimum, R2. So you're going to pivot. That's why this is very important as well. So you know this one is going to enter, this one is going to leave. So the intersection is the one that is going to tell you where to pivot. So the intersection is the one that tells you here this number should be 1. And the other one should be 0. Okay? So when you move from here to here, you know that you're going to pivot here because x1 is going to take this place and R2 is going to leave the base. So from here to here, you make x1 part of the matrix, and you make this one 1 and the other 2 0. Good question. Any other questions? Okay. So let's move to the second problem. The second problem, you don't have to solve anything. The only thing that you need to do is to establish how your objective function is going to look like. So depending on, for the first phase, so depending on how many decision variables or artificial variables you're going to have, that's how your objective function is going to look like. Good? Now, the third problem is just, yeah, that's it. You don't have to, yeah. You started solving them?
Well, I got
Just write the objective function, yeah. Yeah. I think that's why you are having problems. Yeah. And then you are making harder than it is actually. And then for this one, write the phase 1 for the following problem and then solve to show that the problem has no feasible solution. So first thing you do is to make them add those artificial and slack variables that you need for the problem. So you only need one artificial variable, R1. So you minimize R1, and that will give you the coefficients for your first tableau.
Is there any reason you put R1?
No, it doesn't matter. I mean, at the end you'll get the same solution. You can have this column here or that one over there. So this is your first basic solution. Now again, look at the tableau. These numbers, this variable, which is the artificial, still have the coefficient that is not 0. So you have to make that 0 before applying the phase one simplex. So that's the first thing you're gonna do. Now you get this tableau. So these numbers are now 0. So from here you are minimizing, so you're gonna enter the most positive coefficient in row 0, so that's x1. So x1 enters the basic, and now you need to find out which one is gonna leave. So again, you look at the ratio. This one is the minimum ratio, so that means that you're gonna pivot this number, and you're gonna make this 0 and 0. And again, go x2 is now part of the solution. Now you enter the most positive number, so that's this should be x4. Yeah, that's typo. It should be x1. And now x2 is going to enter the tableau on the same spot. So you perform those operations one more time. Yes.
Why is the third line the one half? It shouldn't change, right?
This line, it will change because you're pivoting here. So you multiply times 1/2 because you need to make this one 1. Right? So yeah. So I mean this. Remember, you find the number that you need to pivot and make that number 1. Yeah. And then you make the other two 0. So 1, 0, 0. That line will be multiplied by 1/2 first, and then you perform the other operations. So from there you find that this is the most positive. So again, this is x1. I cannot write on a PDF. So this one should be x1. Then x2 is entering the solution. And this is how the last tableau is going to look like. So you see what's going on, right? This is an optimal tableau. At this point, because we are minimizing, and all the coefficients in the 0 row are negative. But what happened? In this tableau, the right-hand side, or the z-value, is positive. Okay, so this is an optimal tableau. But for phase 1, when you finish the tableau, the objective function value should be 0. And we talked in class what a positive number means for a optimal tableau for phase 1. When you find a positive z-value for your optimal tableau on phase 1, that means that your problem is infeasible. Yes.
So it's okay if the R1 is basic?
Yes, because what you usually do is you find the objective function is 0, right? And now you say, okay, I got my first phase optimal is 0, is a 0 level.
So when you get to 0, you first get
Well, once you find all of them are negative, right? That means that the tableau is optimal. But in order to go to phase 2, that right-hand side, that z-value has to be 0.
Or negative.
Or negative, correct. So if that is not the case, if it is a positive number, that means that phase 1 is the problem is defeated. So you cannot transition to the next phase. If this was 0 or negative, then you can try to take this artificial variable out of the solution.
That's part of phase 1 or like?
That would be part of phase 1. I mean, well, this is still phase 1. This is phase 1, okay? So what you're trying to do on the first phase is to find an initial feasible solution for phase 2. Okay? The way you determine that is by looking at the optimal tableau. So you know that the tableau is optimal for a maximization problem if limits are negative. This is maximization. But you also need to find out the value of the z. If that is 0, that tells you that you're good to go to the next phase. But in this case, that is not true. Okay? So when the value is positive, that means that your problem is infeasible. So remember from here, if the minimum value of the sum is positive, this is phase 1, the LP problem has no feasible solution. Okay? And that was the case we found. Okay? So this was part of lecture 7. We didn't went through a specific example in class, but that's why I gave you that problem in the homework, because I wanted you to notice that, and when that happened, that is why we make this, we mentioned this in class. Okay, so you need to be aware that if it is positive, you need to understand that the optimal solution or the optimal tableau is infeasible. Yes.
If it was a minimization problem, it would be the other way around.
It doesn't matter because phase 1 is always a minimization problem, independently of if it is maximization or minimization. Good question. Yeah.
So, like a special case, like if we got to that last tableau, and in fact if the RHS is 0, so we would move on to making
R1 out of the takeout. Yes.
If we were successful at bringing R1 out of there,
Yes.
but our RHS is positive,
That will be very, very weird. I don't think that's possible, but if that is the case, then you cannot move to the next, because you have a z value that is positive. Okay? So if it is positive, that means that it's infeasible, no feasible solution. Okay? If this was 0, then you can go ahead and try to take R1 of the phase 1 tableau. Okay? Okay, so I'll give you until tomorrow for submitting the homework. If you want to submit today, at the end of the class, that's fine. But if you want to revise your homework, you can keep it and submit it tomorrow afternoon. You can send it by email, or you can leave your hard copy in my mailbox in the office. That will also work. Or if you want to leave it in my office, that's fine. I'm usually there. So okay. So I think we spent good portion of the time explaining how to solve problems using the simplex. You know that the software that we learned, the solver for Excel and other software, uses this simplex method to solve LP programs as well. So what's behind the software is the simplex algorithm that we are learning here in class. Okay? So there's companies that make a lot of money just by implementing those algorithms that you just learned here in class to solve these problems using the computer. Okay? So there's always a lot of research going on in finding best methods or best algorithms to solve these problems, faster algorithms. So once a new algorithm is found, you see these companies fighting for those rights and trying to get the rights from the author to implement those algorithms in their software. So that's something that's going on. There's a lot of people using LP program, finding some modeling these problems. For example, military applications use a lot of optimization, a lot of operation research. So We're talking about a lot of money that is invested in this type of methods and finding new methods to solve linear programming problems. So that being said, I'm going to give you a better understanding of why these problems are so useful. Okay, because it's not only that you're able to solve a problem and find the optimal solution, it's the type of analysis that you can perform using the solution of these problems. Okay, so that will give you a lot of flexibility in terms of how to manage your resources. So if you know your optimal solution, but you also know how to uh, vary or move these resources in such a way that you can decrease maybe a production part of your company and still get the optimal value, you will save some money, or not necessarily save some money, but you know where to invest your resources in an appropriate way. Okay? So there will be some cases in which you can play with your resources and make some changes without affecting your optimal output. And that's the type of things that we're going to discuss here in class. So we went through this last time, so I just wanted to give you an idea of where we are in the class. So we are almost done with these three first objectives, and then we are starting discussing and going through those last two objectives for the course. So again, we're going to discuss how changes in LP parameters affect the optimal solution, and that's what we call sensitivity analysis. I'm going to explain how to use the Excel software. Excel and the other software packages give you a good report in terms of the sensitivity of your problem. So we're going to learn how to get those reports in class and also how to use them to answer questions. And I'm also listing here the readings. If you are interested, you can go in your book and read those specific sections. So we went through this. This is the type of question that you would like to ask, and also you would like to find an answer if you're working in a company. So what is the most money a company will be willing to pay for an extra hour of labor? So if you want to increase your production, how much, what is the most that you will pay for that extra hour? Okay, so we're going to use two methods to explain sensitivity. We're going to start with the graphical sensitivity analysis, and then we're going to transition to the algebraic method. And then lastly, we're going to discuss how to get those reports from Excel. Okay, so the subject matter of this session, the parameters input data of the model can change within certain limits without causing any changes in the optimum. And this lecture explains the basic ideas of sensitivity analysis. Okay, so let's start with the graphical sensitivity analysis. Okay, so this section demonstrates the general idea of sensitivity analysis using graphical methods. And two cases will be considered. We're going to look at the sensitivity of the optimal solution to changes in the availability of the resources. So most of the time, the number of resources that you have in your problem are listed as part of your right-hand side of your constraint. So usually, let's say you have 100 hours of a particular process available. So let's say you have 100 hours of labor. So most of the time, if you want to use those 100 hours, that it's listed as a right-hand side of your constraint. So you want to decide how many of each product to produce, and you have a limitation in terms of your hours of labor. So when I say right-hand side of the constraint, that's what I'm talking about, is this side of the constraint, and that usually limits the capacity that you have in your resources. Okay, so we're going to perform a sensitivity analysis to that right-hand side of the constraint. And the second type is the sensitivity of the optimal solution to changes in unit profit or unit cost. So here we're going to deal with the objective function. So when you look at the objective function, most of the time you're trying to maximize profit, okay, or minimize cost. And you have a particular, for example, if you're maximizing your profit, you have a objective function that usually lists the revenue that you're going to get for selling product 1. So if your revenue is $5 for each product, you're trying to maximize the number of products that you're gonna produce, right? So $5, if you produce 100, that means that you're gonna make $500. So that's when you're trying to maximize your profit. What we're gonna do in this class is we're gonna see how, if I change this profit number to 7, would that change my objective, my optimal solution? Let's say that I have multiple variables and I decide to produce 100 of X1 and 200 of X2. If that is my optimal solution, 100 and 200, if I change the profit that I make from product 1, would that change my optimal production schedule, 100 and 200, or will I have a different production schedule? That's the type of question that we are going to be able to answer. So let's look at a particular example. So I decided to show you a typical example. So most of the time, if you're working a production, this one is, I think, is a computer type of maybe boards for computers. You have a machine that is usually the one that is your bottleneck, basically. It's the one that dictates how many units you're going to be producing. Okay? Because if the machine is able to hold a unit every 5 minutes, you don't want to put a lot of units before the machine because that will create a queue. So we are looking at 2 machines in the next example. And so we are manufacturing 2 products on 2 machines. A unit of product 1 requires 2 hours on machine 1 and 1 hour on machine 2. For product 2, 1 unit requires 1 hour on machine 1 and 3 hours on machine 2. So we have 2 different sequences for the 2 different products. So the revenue per unit of product 1 and 2 are $30 and $20 respectively. And the total daily processing times available for each machine is 8 hours. So we are looking at it on a single shift, 8-hour shift, and we need to decide how many units we're going to produce from each product. Okay, so this should be a very easy problem to formulate. We know the revenue that we're going to get for producing each one of the products. So let me start by defining my decision variable. So xi is the units produced of product I. Okay, so x1 represents the first product, x2 represents the second product. So from here I can formulate my objective function. So we have the revenues per unit, $30.20. So what will be your objective function for this problem? You want to maximize, minimize? Yes, you want to maximize your profit. And you know how much you're going to make for each unit. So max Z equals 30x1 plus 20x2. And this has two constraints, one for each type of product. So we have that a unit of product 1 requires 2 hours on machine 1 and 1 hour on machine 2. And product 2, 1 hour requires on machine 1 and 3 hours on machine 2. So we can have a constraint for each machine. So for machine 1, we have 2 hours for the first product and 1 hour for the second product. And we have a capacity limitation of 8 hours. So this is machine 1. And then for the second machine, we have x1 plus 3x2 less than or equal to machine 2. x1 and x2 should be greater or equal to 0. Okay, so we are trying to maximize our profit, and we want to use our resources in the optimal way so we can maximize our revenue. Is that clear? Okay, that's what we're trying to do here. We have two constraints, one for each machine. We know how many hours we have available for each machine, and we are trying to maximize the profit. So if you solve this problem using the graphical method, this is going to be your visual region. So we have the constraint for the second machine here, and we have the constraint for the first machine here. Okay, and we also have the non-negativity constraint, so x1 should be greater than 0, x2 should be greater than 0. So that's why this area is limited to this side. So the optimal solution using the graphical method will be here, and the optimal will be x1 equals 3.2, x2 equals 1.6, and the optimal solution will be 128. Okay, so I'm assuming you know how to find the optimal solution, so that will be the optimal solution. Point C. Okay. So now I have a new graph here. The new graph illustrates the change in the optimal solution when the changes are made in the capacity of machine 1. So machine 1, the constraint for machine 1 is this one, the original one is this one here. Now I'm moving that constraint to the right. So this constraint is now shifted to the right. So if the daily capacity is increased from 8 hours to 9 hours, the new optimum will move to this point here, G. Okay, so what will happen is the following. We are adding an extra hour of capacity. So instead of being less than or equal to 8, now this constraint is less than or equal to 9. By making that simple addition or modification to the constraint, if you look at the graph, that constraint is going to be moved to the right, and the visible region, is it the same or will it change? It's larger, right? Because if we don't have this constraint anymore, this extra space is going to be part of the visible region. So by adding that unit of hour to my first constraint, I'm adding that portion of the graph to my visible region. So now my optimal solution will move from here to here, and the value will go from 128 to 142. So you are maximizing your profit. Kind of makes sense. You add an extra hour of production, then you should be able to increase your production. and you should be able to increase your profit. So this solution makes it. Okay? Now, the rate of change in optimal resulting from changing machine 1 capacity from 8 to 9 hours can be computed using the rate of revenue change. Okay? Any idea of how would you compute this change or rate of change from one point to another in this line? Correct. So that's the slope of the line. Okay? Any other definition or concept that you know? The derivative. Correct. So we're going to look at the slope or the derivative of that particular line. So we go and look at the slope. So let me make a note here. Slope or derivative. And in this case, for the example we are looking at the slope from G to C. So Z of G minus Z of C divided by the capacity change, and that will be 142 minus 828 divided by 9 minus 8, and this equals $14 an hour. So, yes. Here? Capacity change. Yeah. Sorry. Yeah. So you have an initial capacity of 8. Now you're adding an extra unit, so the change will be 1 hour. And you have the difference in terms of the optimal values, so 142 and 120. So that change, that rate of revenue change is $14 an hour. So that means that for every hour that you add for this resource, you will increase your rate of revenue or the revenue of your objective function by $14. Okay, and that's what happened here. Okay, so now if you have not seen it before, one of the things that you can do using the derivative or the slope is that you can compute the rate of revenue change in linear program. Okay, so the name unit worth of a resource is a description of the rate of change of the objective function per unit change of a resource. So early LP developments have coined the abstract name dual or shadow price. And those are the names that we're going to be using in class. So a dual price or shadow price is the unit worth of a resource. It basically is the rate of change of your objective function by adding or taking out a unit of resource from your problem. Okay, so this name is now standard in all LP literature and software packages. By looking at the graph, we can see that dual price of 14 hours remain valid for changes, increases or decreases in machine 1 capacity that move its constraint parallel to itself to any point in the underlying segment B and F. So I'll give you a chance to write that down, and we're going to see how that is applied to the graph. Okay, so you saw how moving that constraint parallel to the original one, by moving that constraint to the right, you were able to increase the optimal value and the revenue you were making in your problem. So what we're saying be able to affect your objective function value if you move this constraint along this line, because that will be changing your visible region. So that line can be moved to up to F, and also can be moved all the way to D. And you'll see how that visible region will change. Okay, so if you move it to this side, this is your new visible region. If you move it to that side, it will be the whole triangle. Actually, no, it's just that point. Okay, because no, it's the whole triangle. Yeah, it's the whole triangle. Sorry. Okay. So I think the next slide is just a repetition of what I just said. So the dual price, machine 1 capacity, parallel to itself to any point in line segment B in it. Okay, so that's what we saw. It's gonna, but we can see that dual price of $14 will remain valid for that line if you move that constraint. Okay, we compute machine 1 capacity at point B and F as follows. Okay, so I want to know what will be the capacity on each corner of that line. So the minimum machine 1 capacity at B, which is the left corner, that point B is x1 equals 0, x2 equals 2.67. So I'm going to use a constraint for the capacity of machine 1 to compute the capacity. So that constraint is 2x1 plus x2. This is coming from machine 1 constraint. Okay, so the minimum capacity at that point will be 2 times 0 plus 2.67. And that is equal to 2.67 hours. On the right corner, F, the coordinates of F are 8 and 0. So the maximum capacity of machine 1 will be 2 times 8 plus 0, and that will be equal to 16 hours. Okay, so the conclusion is that the dual price of $14 an hour remains valid in the range 2.67 hours less than or equal to machine 1 capacity less than or equal to 16 hours. Also, any changes outside this range will produce a different dual price or work unit. Okay, so this dual price or $14 an hour, that change will be only valid again on this line. This is point B, 0, 2.67. This is point F, 8, 0. So that rate of change of $14 an hour will be valid if the machine capacity is within those capacity hours. If it is outside those capacity hours, then the dual price will be different. Okay? So, using similar computations, you can verify the dual price for machine 2 capacity is $2 an hour. So you can perform that, find the slope for the second machine, just like we did here. And That will remain valid for changes in machine 2 capacity within the line segment DE. We can also compute the machine 2 capacities at point D and E as follows. So we know that the constraint for machine 2 is x1 plus 3x2. So this is machine 2. So the minimum machine 2 capacity, that's point D, will be 1 times 4 plus 3 times 0, and that is equal to 4 hours. And at point E, we have 0.80. So the maximum machine 2 capacity will be 1 times 8 plus 3 times 0, and that equals 8 hours. So again, the conclusion is that the dual price of $2 an hour remains valid in the range 4 hours less than machine 2 capacity, and in 20 this yeah, this is wrong. It should be 0, and this should be 8. And this will be 24. Check the graph one more time. So it would be 9. Yes, so this would be 0, 8, 0. So this point is 8, 0. And this one is 0. This one will be 0, 8, 0, 0, 8. And this one will be 4, 0. Yeah. So, yes. So here we have, yeah, it should be 0, 8. So you can make that change. It should be 0, 8, and the total should be 24 hours. Okay, so the computed limits for machine 1 and 2 are referred to as the feasibility ranges. All software packages provide information about the dual prices and their feasibility ranges. So you'll see that when we implement a problem using Excel. Excel will provide you with the sensitivity analysis. The dual prices allow making economic decisions about the LP problem, as the following questions will demonstrate. Okay, so now comes to the Q&A part of the class or lecture. So let me see if you can take what I showed in the lecture and use it to answer these questions. Okay, so question 1. If job scope can increase the capacity of both machines. Which machine should receive priority? And for this, you will have to think about the rate of change. So you notice that when you move, you add an extra hour of capacity for machine 1, your profit increased by $14. When you increase the capacity of machine 2, which is the rate of change for machine 2, your profit increased only by $2. So by using those two figures, which one should have priority? Machine 1, right? Because it's the one that is going to increase your profit faster. Okay, so each additional hour of machine 1 increases revenue by $14 as opposed to only $2 for machine 2. And that's only looking at the dual price. Okay, so if you have that type of decision in your hands, you look at the dual prices, and you see easily you can see the difference in terms of the revenue. So you would prefer to add 1 hour of capacity to the first machine. Okay. Question 2. A suggestion is made to increase the capacity of machine 1 and 2 at additional cost of $10 for each machine. Is this feasible? Would you recommend this? Because increasing the hour, let's say you want to add an operator for your machine. That would cost you $10 an hour. If you want to add that person, or if you want that person to work that extra hour. That costs you $10. Would you add an extra hour for both of the machines, or only one, or none of them? Yes, correct. So for the first machine, you can add that cost. You will still have a $4 profit. But for the second machine, if you have a cost of $10, then you're going to affect your revenue because you're only making $2. So the answer, of course, for machine 1, the additional net revenue per hour is $4. But for machine 2, the additional net revenue per hour is negative $8. So that would not make sense in terms of your revenue. So only machine 1 should be considered for capacity increase because it's the only one that is going to provide you with some revenue. That makes sense? So let me know when I can go to the next. So as you can see, the first question basically makes you to make a decision between one or the other. The second question is just for both of them. You have the chance to increase the capacity. Would that be admissible or not? Then you make a conclusion based on the dual prices. Question 3, if the capacity of machine 1 is increased from 8 hours to 13, how will this increase impact the optimal solution? Would you be able to compute that? So you saw that an extra hour gives you $14. So if you have 5, that should increase your profit by 5 times that 14 hours, or that $14. Okay, but first, you need to find out if the dual price is applicable for this size. So you know that dual price will be applicable from 2.67 to 16 hours. So if you go to 8 to 13, that dual price still applies. Okay? So based on that, then you can say that the proposed increase to 13 hours falls within the feasibility range. So you will increase your profit by 5 times 40, which is $70, and the total revenue will be increased from $128 to $198. Okay, so again, that's why you need to find out those lower and upper bounds for the dual price, because in the case, instead of being 13 hours, if that were 19 hours, then you know that 19 hours is not within this range. So your dual price will be different. And we're going to learn how to compute that in our next topic. But for now, find out if the range applies to that capacity. If that is true, then you can say, okay, it's within the capacity limits. So I know if I increase the unit of hours, I still have the same rate of change. So I can increase my profit. And that's what's going on here.
What happened to the price of
the price of running in, so that's why that was basically what we were trying to capture in this second question. So you know you will have some cost by adding that extra hour, so that could be part of this. Okay? So that's why you need to take those things into account. So if you were running by $10, if that were to be applied here, then instead of 14, it will be $4 profit. Okay? Good question. The fourth question is, suppose that the capacity of machine 1 is increased to 20 hours. How will this increase or affect the optimal revenue? So again, we have to refer to these bounds. So the proposed change is outside the feasibility range. So further calculations are needed to find the answer, and that will be part of our next topic. Okay, so for now, this is all you can say. You cannot make a decision or make a recommendation because based on what you know, it is not within those bounds. So you don't know what will happen if you go outside those bounds. Okay, so that's all I have for today. Again, make sure that you submit your homework. You can scan it, send it to me by email. You can submit your homework, put it in the mailbox. You'll give you until tomorrow, 5 o'clock, to do both or either one. And again, if you have questions about your homework, don't wait until the last minute. You can always send me an email or stop by my office or just try to reach me, because I probably can answer that question, and that will help you work with the homework really quick. Okay, so as you saw, homework was not hard. The only thing is, if you don't understand the details, then you will get stopped doing those tableaus over and over again. Okay? So I'll see you on Tuesday, and please submit your homework by tomorrow. Thank you.